a simple Rankine cycle uses. I'm going to read that for you later. So let's go to the notebook. So to save time, I've written some stuff before. As I told you, we are now limited about cycles, okay? So, and each cycle consists of different processes. And we need, for each process, we need to indicate the initial and final states by just calling like number 1, number 2, 3, and 4 and stuff. So when we talk about power cycles, the working fluid might be a gas that, like in power plants or in aircraft engines, it's a mixture of air and fuel, right? So it's a gas. And on the other side, we can have something like like water, H2O, or like refrigerant. So like R134A, yeah, that one. Because we're gonna deal with different phases of this material. It might be liquid, it might be a liquid vapor mixture, or it might be like subcooled or like compressed and like superheated, right? So there are different phases of this material in vapor power cycle, which is called Rankine. So here on the left side we have Brayton cycle. Um, it's just we have other types as well in the gas power cycle. On the right side we have vapor power cycle, which is the Rankine. So let's talk about the Brayton first. So as I told you, in Brayton cycle, the working material, working fluid is air, right? So there's a major difference in between Brayton and Rankine, and that is the how do we compress this fluid, right? On the left side, the working fluid is air, so we need to use compressor to compress it. But on the right side, we have something that can be in a liquid phase, so we use a pump to compress it. So this is a major difference in between these two different cycles. In Brayton cycle, we have a compressor here, and it's connected to the heat exchanger, which is in like a red box. It's just to show that it's hot and we are adding heat in this process. And then it's connected to the turbine, then the gas expands and does work, and then it will go to heat exchanger to reject the heat, cools down, and go to the compressor, get compressed again, and completes the cycle. So this is this would be the direction of the working fluid in the pipes. Okay. And since I know that I have four devices, so I would have four processes, and each process has like one initial and one final states, and I'm gonna call for compressor the initial point is 1, the final is 2. For heat exchanger, the hot heat exchanger, the initial is 2 as well, so it's gonna be shared in between compressor and heat exchanger. And the outlet of this guy is number 3.3, which is shared as the inlet for the turbine. And likewise here I have point 4, which is the outlet of turbine and inlet of heat exchanger. And these two cycles are just the simple types. We can have like different types that are more complicated, but I'm not going to talk about those here. In the hot heat exchanger, we add heat, so Q in, and the cold in this one, in the cold one, we reject, so Q out. We reject the heat. And turbine and compressor in most of the cases are connected through the shaft. Here's the shaft which connects the turbine and the compressor, and then the outlet we get the work out as the shaft work. So that would be the net work, which is in our equation. If you check our lecture about Brayton cycle, you'll see all the equation and stuff. And this work, W out, W net out, equals W produced by turbine minus W consumed by compressor, because they are installed on the same shaft. And on the right side, we have the Rankine cycle, and here the working fluid is water, so it might condense, it might boil, uh, or like it can go to like superheated state or subcooled, like there are like different, like a variety of different states for this material. And likewise, we're gonna have here point one, outlet, condenser outlet, pump inlet. Two, pump outlet, boiler inlet. Three, boiler outlet, turbine inlet. And point four, turbine outlet, condenser inlet. Therefore, that is gonna be the direction of how this cycle happens. In the boiler, we know that it's like in a like a stove, for example, right? And we have flame or something that warms up the water. So we're adding the heat, Q in. Likewise, as we have, same as what we have in the Brayton cycle, right? But I'll tell you later. And then here we have the Q out in the condenser because it's like a freezer, like a refrigerator, that you just like withdraw, you take out all the heat and you cool down the fluid, the working fluid, so it condenses. Um, so once again, the differences about the differences between these two different cycles. Why like in the why do we call boiler, right? It's basically a heat exchanger. What? But when we talk about heat exchanger, we want to just emphasize that it's gas. Like you cannot boil gas. You know. So and also like when you're talking about water, it makes more sense if you say I'm boiling the water. I'm like, okay, okay, I got you. But if you say like I am in a heat exchanger just to add heat to the water, it's like, you know, you could have said that in like two words or one word, boil it, you know. And likewise in the condenser, you can just I'm condensing the vapor, so it condenses, and then the state would be like liquid, saturated liquid, for example, or subcooled liquid. That's understandable. So now let's go to the figure, to the plots. On the left side, once again, we have air as a working fluid, and on the right side, we have water, H2O. And I'm plotting the TS diagrams. Okay, so here's the T, the vertical axis, and the horizontal axis is the entropy. Now, let me see if I can have both in. Just keep in mind that here these horizontal axes are entropy. And let me double check if it's working. Okay, great. So that's good. That's good. So let's start with the process 1 to 2, point 1 to point 2, which happens through the compressor. We assume that the compression rate, that the compression happens isentropically, so the entropy does not change, and this horizontal axis was it represents the entropy. So if I call that point here point 1 and point 2 on top of that, then that would be a vertical line, and it shows that entropy here is constant. See, from point 1 to point 2 we are at the same entropy. And meanwhile, during this process we are compressing the gas and we are injecting this work. So this is work, compressor going into the system, into the working fluid, on the working fluid. Then if you go further to the heat exchanger, the hot heat exchanger, we know that here we are adding the heat. So Q in. And this process is going to end up at point 3. And these dashed lines, this curve, this red curve, represents that pressure is constant. So in a heat exchanger, pressure is constant. So P2 equals P3. Then let's go to the turbine, and likewise, as I said in the compressor, we assume in an ideal ideal Brayton cycle, the expansion would be isentropic. So point 3 would be exactly on top of point 4, right? So entropy would be constant, and the turbine is doing work, so we get this work out. That would be W turbine out. And to complete the process, to the cycle, we need to go to the cold heat exchanger just to withdraw Q, and we complete the cycle, right? So here's the direction. Go up, go there. Temperature is increasing. You are adding the heat to your working fluid. Then in the turbine, it does work, and then go back to the first point, which is point one. I'm not gonna spend much more time on this topic. I'm just because this the focus of this, the aim is just to talk about Rankine cycle. So let's go to the other one, right? Now we're gonna talk about boiler, condenser, pump instead of compressor, and turbine is still there. So I'm gonna start with the process 4 to 1, which is here. 4 to 1 happens in the condenser because then it makes much more sense. Um, so point 4 in a point 4 to point 1. So let's think a little bit more about the concept of condenser. The condenser is like, let's say you have a mixture of liquid and vapor and you just want to somehow do something that it ends up with only liquid. So you want to condense the vapor phase, right? So you can like use some like cold tubes or stuff that you can send this vapor steam, you know, in between these tubes, cold tubes. Then like at the surface of these tubes, it condenses and it drips. Those droplets generate and it drips down, probably in a container. So that would be the whole concept of the condenser. And when you like in an ideal Rankine cycle, um, point one, which is the outlet of the condenser, would be a saturated liquid, right? Because you're just basically, what are we doing? We are condensing a vapor, and as soon as it gets to the liquid, the phase changes to the liquid phase. Then that's what we want. We want water. We want liquid. So at that point, the quality would be X would be zero because it's all liquid. There's no vapor anymore. So point one in an ideal case, point one would be right there on this curve, on the left side of the curve, which represent the saturated liquid. So here's point one, and point four might be anywhere on this line, which is like a mixture of vapor and liquid, right? We don't know anything about point four. Is always a question. It's like a mystery that we need to discover in our solutions. So, and since in the condenser a phase change process is happening, so we know that in a phase change process temperature is temperature is constant. See, it's a horizontal line, but we might subcool point one. We might go lower points like there. We might do that, which actually in this example that I'm going to talk about, we do it. It says that condenser subcools the vapor. Anyway, but we are sure that pressure is constant. So pressure is constant and we will be on this dashed line curve. So in the condenser, pressure is constant all the time. Then we move to the pump, and in the pump just pumps, right? Pumps the liquid, and we can let's assume that it's isentropic, so entropy remains constant, and we're just from like this dashed point, red dashed points, we go up to another pressure, another dash point. So we're just changing the pressure. That's it. We're just pumping. It's like pressure goes up. That's it. That's all we're doing basically. No other change. And we are adding the pump work, pump, which goes in. Then we have, what do we have? We have like liquid at high pressure and it's ready to absorb energy, right? So we send this guy to the boiler and we say, okay, now you're at a high pressure. That's awesome. All you need now is a high temperature. So let's warm up this guy. Let's add heat to this guy. Therefore, it's gonna boil. Pressure would be constant because it's a phase change process, and the all changes would be in temperature. Temperature is increasing. So from point one on this black curve, we go here. Pressure is constant still because it's phase change. In the boiler, you are boiling. Keep in mind when you're talking about boiling or condensing, these two processes are phase change, and in phase change, pressure is constant. So from point 2 to point 3 on this curve here, black curve, then a constant line, and then we can, here's optional, we can end at this point with a saturated vapor, or we can just add more heat, right? We can just warm it up more, and we can go at higher temperatures. See, this vertical axis is temperature. We can go at higher temperatures and we might end up at this point. It's optional, I'm telling you. You might you might finish it at that point with the saturated vapor, or you might go a little bit higher. Again, point 3 is another mystery because we don't know. It might be mentioned on the text, it might not. So we need to investigate. We need to check the tables based on, like, we might have pressure and temperature. That's enough, two intensive properties. So we can go to the table and look for the state, right? I'm gonna do it actually in the example. And then just we complete 3 to 4. That's it. So here in the boiling, we add heat, Q in, and from point 3 to point 4, likewise, this is a turbine. The turbine in between Rankine and Brayton, they're the same. It's just turbine. Basically, let me tell you something. Actually, in the Rankine cycle, we have steam, right? And steam is a gas, some sort of. So it's like here the gas in turbine in the Brayton cycle. But I mean, like, we are just getting out this work. We just want that pure work that might be like a shaft work again. So here's the work, the turbine work out. Awesome. Now I want to give you a summary about. Let's go back to gas power cycle. So in the examples about gas power cycle, Brayton cycle, um, we had two choices: constant specific heat, CP and CV, or variation of specific heats. I'm just giving you a summary. So in a constant specific heat approach, we could use these relationships, right? And then we can heat, like, CP and CV are constant, so it's safe to say delta H equals CP delta T, and delta U equals CV delta T. But if the constant heat, I'm sorry, the CP and CV are changing, then we need to use this table A17 in the textbook, in the central textbook, and then we can go that, okay, this is the ratio. I've done this in other examples. If you want, you can check our other lectures. And here is for specific volumes, that these are relative volumes, so we could use these guys. And delta H, now we cannot say it's CP times delta T because CP is not constant anymore, so we need to directly use the tables, this table A17, and we should use, okay, delta H is like H2 minus H1. Simply read H2 and look for H1 as well in the table, and internal energy is the same. You cannot use those equations anymore. CP delta T, CP delta T. No, 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 no. You cannot. So all these equations are about Brayton cycle. If you are solving a Rankine cycle, oh my God, I've seen a lot of students that get confused and they don't pay attention that they're solving for a Rankine cycle, and they use like CP, what do you mean? It's like you have liquid, CP, like, you know, all that we have been talking about in this course, actually, when we CP is for, mostly, in most of the cases, CP was for gas, right? And now you're talking about a pump, so how do don't get confused, okay? Um, Yeah, so all these stuff are just only on the left side, are just only for air, gas, like gas power cycles, Brayton cycle, Otto cycle, diesel cycle, you know. But if you're talking about a Rankine cycle, the story is totally different because you have phase change. You're dealing with liquid, then you go to vapor, then it's superheated, you know. You cannot, it's another story. It's totally another story. That's why I'm just trying to have them on the same page, you know, beside each other to differentiate it clearly for you, just to prevent confusion in the exam or when you're solving an example. Anyway, so I'm gonna start with process 4 to 1 and 4 to 1. See, 4 to 1 is condensing, 1 to 2 is in the pumping, 2 to 3 is boiling, 3 to 4 is in turbine, which is an expansion. Okay, so in process 4 to 1, which is condensing, we have phase change. Therefore, pressure is constant. Right? Pressure is constant. P1 equals P4 in the condenser. As I told you, point 4 can be at any status here. Point 4 can be a mixture with any quality. X4, I have no idea about that. I have no idea about that. So point 4 can be anything. And about point 1, because point 1 is the after the condensing happened, then uh, in most of the cases when we have an ideal Rankine cycle, then point 1 would be a saturated liquid, right? In most of the cases. So let's say point 1 is a saturated liquid, therefore x1 equals 0, unless the question tells you that it's subcooled. If they don't say anything about subcool and like, you know, just saying it's an ideal Rankine cycle, then point 1 would be here. Unless it is subcooled. That would be mentioned. If it's not mentioned, that would be an ideal. And it's condensed. Work is 0. 4 to 1. Work is 0. It's just condensing. It's just phase change. And the amount of heat that we are rejecting out of the working fluid would be the difference in enthalpies, right? H4 minus H1. Someone might ask, what about H1 minus H4, right? And I would say that, okay, listen, we are just talking about the values of Q. When I say Q out, yes, it's a negative thing because it's rejection. But I'm just talking about the values, and I want everything to be positive. I am gonna take care of the sign later. All these parameters should be positive. This is what I prefer. This is it's much more simpler, simpler. Oh my god. So Q out is a difference between the enthalpies. So now let's compare the enthalpies between point 4 and point 1. Which one is higher? Okay, I have a condenser and I'm withdrawing this heat. So H4 should be higher. Okay, so H4 minus H1. This is obvious. Then now, if I go to the other process, which is 1 to 2, and process from point 1 to point 2 happens in the pump, then I assumed it's an isentropic process. Isentropic, right? S is constant, entropy is constant, and all properties would be at the saturated liquid. Therefore, we use like HF, or we use like VF, or T is at saturation, or P is at saturation. I assume that you remember when we subcool a liquid, all the properties would be chosen at temperature, specific temperature. Pressure does not matter anymore because the liquid is incompressible, and when you change the pressure, just the potential energy is like it's just pressure is changing, right? But when you read for the properties, you should go at specific temperatures. I'm gonna show this in when I'm solving for in the example. Mm, so and therefore we are just changing the pressure. So we assume that okay, we have, let's say we did not we did not compress anything, we did not subcool anything, and it's just saturated values like temperature is saturated temperature, pressure is saturated pressure, and the values for enthalpy, internal energy, and specific volumes would be all for saturated liquid, but at different temperatures. I will show you more about that. And in a pump, there's no heat. Q is 0. It's just work. And how do we solve for work? W pump in. Let me write it this way. W pump isentropic. Because I'm assuming that process 1 to 2 is just a straight vertical line from point 1 to point 2 right above it, and entropy does not change. And assuming that, okay, the process is isentropic, then I can say, well, okay, so it's like H2 minus H1 equals V1 or 2. Again, doesn't matter because it's going to be VF times difference in pressures, P2 minus P1. And in the next process, which is from point 2 to point 3, and that would be boiling. The previous one is in pump. So condensing, pumping, then boiling, and the next one would be expansion in the turbine. So this process point 2 to point 3 is boiling, phase change. And pressure would be constant. Therefore, P3 equals P2. And we might have, it is a plus. We might have plus superheating, right? You remember I told you about point 3. Point 3 might end up at this point on this line here as a saturated vapor, or it might go up a little bit more just to superheat the vapor. It's optional. It would be mentioned, or we need to specify that by checking in the tables. So it's a boiling process. Work is gonna be 0 because it's just a simple phase change. And Q, how much of heat we are adding to the system, is the difference between the enthalpies. And after adding this heat, which is point 0.3, we would have higher enthalpy, so we write H3 minus H2, not H2 minus H3. And the last one, just to finish the cycle, complete the cycle, is from, so process point 3 to point 4. And point 3 to point 4 happens in the turbine, here 3 to point 4. And that's going to be an isentropic process, we assume. If it's not, then I'll show you in the example. So this is an expansion, right? And S, it's isentropic. Okay. And its turbine is adiabatic. Q is 0. and work turbine. Again, we assume that that is isentropic process. So then that would be H3 minus H4. Okay? Assuming that in the turbine and in the pump process was isentropic, then we can use those equations. Otherwise, we need somehow to incorporate the efficiencies that will be um, mentioned in the example. I guess that's all. If you want to know more, then please check. Um, Let me write it here. So in vapor power in Rankine cycle, you can check this lecture 21, page 4. For here in Brayton, you can check out this lecture for number 14, pages 5 and 6. Okay. So I think that's all for introduction and like the concept of the comparison between these two different cycles, and we're gonna talk about the Rankine cycle in this example. I hope that you're not mad at me, you're not bored, or like tired. Please, you can pause now. You can pause, go like have a coffee or like I don't know, just rest a little bit and then come back, and then I'm gonna solve an example because in the example I will refer to like a lot of these equations and I'm not gonna talk about assumptions anymore. You can, if you have any question, you can play it back from I don't know a couple minutes before. And uh, thank you so much for listening so far. So that was all about concept and stuff, equations and formulations, and let's go to our example. So as always I'm gonna read the example. How many minutes? Oh my god, we passed half an hour. Okay, I'll be quick. So I'm gonna read the example for you, and you're supposed to do this when you are in taking an exam or you're solving an equation, solving an example, because you need in the beginning you need to get a good perspective, a good imagination about the whole story in a block. And then you can decide, you can like relax and just decide, okay, which question I'm going to talk about. Is it a gas power cycle? Is it a vapor power cycle? Rankine, Brayton? What is it? What equations am I allowed? I'm allowed to use, what equations I'm not allowed to use, and like which tables. Is it like the working fluid is water or is R134 and all this stuff. Okay, the question says a simple, listen, simple Rankine cycle uses water, okay, as a working fluid. The boiler operates at 6,000 kPa and the condenser at 50 kPa. So we know that those red dashed curves, which represent constant pressure processes, one which is about boiling at a higher pressure is 6,000 kPa. Imagine 6,000 kPa, and the other one, which is the condenser, is at 50 kPa. Sorry. At the entrance to the turbine, the temperature is 450 degrees C. Okay. The isentropic efficiency. Oh my god. Oh my god. When you see isentropic efficiency, it means that either the pump or the turbine are not working ideally. So there's a efficiency going on. The isentropic efficiency of the turbine is 94%. Okay, that's a good turbine. Pressure and pump um, losses are negligible. So pump is a ideal pump. So the what is it? The efficiency would be 100%. And the water leaving the condenser is subcooled by, see, it's subcooled. So when you pass the condenser, the temperature would be 6.3 degrees C lower than the saturation temperature at the corresponding pressure, which is 50 kPa. And it adds that the boiler is sized for a mass flow rate of 20 kilogram per second. Whenever that you read a sentence about mass flow rate in an example, it means that all the parameters that you pick, you pick from the tables. All these parameters are in the unit of kilojoule per kilogram. And now the mass flow rate is provided. So if you multiply these two parameters, like m dot times little h, then how would the units be? The units are, for m dot, it's kilogram per second, right? Kilogram per second times kilojoule per kilogram. So the kilograms canceled out, and you'll end up with kilojoule per second, which is power. So now, when you see the flow rate, you should be suspicious. You should see, oh, okay, so I have the mass flow rate, so I have a link in between all those little parameters, little h, little u, little v, you know? I can have this link. I have this link in between these parameters and rates, powers, like capital Q dot, which is the rate of heat going out. It's like kilowatt, or W dot, everything, all this. So the mass flow rate is provided. Then it asks for a couple questions, and the first one is determine the rate. See, the rate. When it says rate, it means kilojoule per time, per second, kilojoule per second. So we have to use mass flow rate. Determine the rate at which heat is added in the boiler. So it's capital Q dot in. So when we okay, so I need to use this first page. I'm gonna write a lot of stuff. So in cycle problems, in cycle examples, we need to have a huge summary table, because we're gonna update this table several times. And I swear, I'm telling you, if you use this summary table, you are gonna do it. You're gonna be successful. You can solve the whole example, no matter how long or how complicated it is. You can use it. All you need to know is just a table that shows you clearly what you have and what you don't have. That's it. That's it. Simple. And you have like 10 values. You cannot like search for each in during your solution. It takes up all your time. Anyway, I don't wanna. One, two, three. Okay. So, oh my God, again, it's difficult. I didn't do a good job. So I have 4 points, right? Point one, two, three, four. Point one, point two, and point three. At the end, point four. What do I have? I have the pressure in the condenser. So in the condenser, inlet and outlet are point 1 and point 2. So I have P4 and P1. P1 is 50 kPa, and I have P4, which is the inlet of the condenser. P4 equals 50 kPa. What else do we have? We have the pressure at the boiler. The boiler was up there, here, the whole process, 2 to 3. And pressure is constant, so P2 equals P3 equals, what was that? 6,000. Okay, so P2 equals 6,000 kPa, and pressure is constant in the boiler, so P3 would be similar to P2. Oh my God, 6,000 kPa. What else do we know? It says that the temperature at the turbine inlet, which is point 3, is 450 degrees C, and the condenser subcools the liquid 6.3 degrees C lower than the saturation temperature. So T1 would be the saturated temperature at 50 kPa minus 6.3 degrees C, which would be 81. This is off the table. A4, I guess, minus 6.3, which would be 75 degrees C. This is T1. We have T1. And that's all we know. That's all we know. And now here, I need to draw um, the TS diagram for you just to make it more clear to show you what is happening. So since we have the material, the working fluid is water, so we need to include the saturation lines in the please in the gas power cycle. There is no saturation line. Please don't do it. When you are solving for Brayton, auto, diesel, jet propulsion, there is no saturation line because there's no phase change. It's air, and air remains air. It doesn't condense, at least in the temperature limits that we are working at. It's gas. There's no saturation line. But here in Rankine cycle, yes, yes, because we condense it. These are constant pressure in the condenser. Here is constant pressure in the boiler, and here point 1 is subcooled, so it's not here it's not on this here anymore. It's a little bit lower, but still pump is isentropically working. Point 1, point 2, and then in the boiler we are having a phase change, and then oh my god. First question. Should I stop here or should I go more? Go upper. Point 3, I have only pressure and temperature, which means that, oh my god, sorry, I forgot to tell you something. I have the efficiency of the turbine, which is 94%. I have the, sorry, what is going on? I don't know, this is the noise. Compressor, oh, sorry, pump, which is 100%. I don't know where is this noise coming from. I'm sorry about that. It's 100%, and the mass flow rate is 20 kilogram per second. Okay, so now I was looking for point 3 if it is here at the saturated vapor, or it's a little bit higher. Um, so at point 3, at point 3, the saturated temperature at 6000 kPa is what? So if you go to the table here, at 6000 kPa is this highlighted row. It's 275.59 degrees C, which is much less than T1, which is 450 degrees C. So it's what? It's superheated because the temperature is much warmer, superheated. Therefore, I need to go a little bit higher, right? Like there, here. So I pass the saturated vapor, and then the turbine is not working isentropically. So the entropy is gonna change. Oh no, no. Don't do that. Don't do that, please, please. Okay. So the entropy, oh my god. Sorry. I'm so sorry about that. Okay. So the entropy is gonna increase. Let's say here is 0.3. So that would be, so let's say here we assume that what would happen if turbine was working isentropically. Then it means if here is 0.3, then we would end up at 0.4 S, which shows isentropically. But now it's not that. Oh my god. But now it's not that, right? Please just these little guys. Okay, it's not that because so entropy increases. This is T temperature versus entropy. So we will end up with at higher like that. No, I didn't like it. There. So we have a little bit like deflection of isentropic vertical line. So here would be zero point 0.4 actual, right? And then in the condenser, we have the phase change and the subcool here. That's it. Dum, dum, rum, rum. Add heat, reject heat, uh, work turbine out, pump in. That's all. That's all. That's all. That's all we want. And here pressure is 6,000 kPa on this curve, and here is 50 kPa. Dun-dun, dun-dun. That's it. That's it. And it's superheated. I guess I've done all. So now let's solve for Q dot in. How much of heat, the rate, so the unit is kilojoule per, is kilowatt basically, and it happens in process 2 to 3 in the boiler, and I know that Q dot in equals the mass flow rate times little Q in, which is, I showed you before in the equations, it is H3 minus H2. I have m dot, I have nothing, none. So now we know that I should solve for this guy. At point 3, I have pressure and temperature, two intensive properties. And I know that it's superheated. So if I go there to this table, 6 megapascal here. 6 megapascal at that temperature. Here's all I want. I want enthalpy, and I'm gonna need entropy in future, but just please, just stay with this. I'll show you, I'll tell you later why I'm picking entropy at the same time. Therefore, H3 at 6,000 kPa and 450 degrees C based on the table would be 3302.9 kilojoule per kilogram. Everything is in per mass because it's a little, they're all little, here's a table, little parameters, specific parameters, and H3, oh my god, at 6,000 kPa and 450 degrees C would be 6.7219. What's the unit? Kilojoule per. Tell me. Kilogram dot Kelvin. Awesome. So now I need to solve for H2, right? Huh. How? Let me update my table first. H3 was six one seven two 19 kilojoule per kilogram Kelvin. Okay, this is what I got so far. Now at point 2 I just have the pressure, and it's not enough. It's not enough. And also I have the efficiency for pump. So somehow I need to do a trick or something, because yes, the efficiency is 100, but let's let's pretend that it's not in the beginning, because I want to introduce the equation for pump efficiency. So now I'm looking for H2, okay? And for pump, this is how we define the isentropic efficiency. That it is the work, isentropic work for pump, divided by actual work. We know that a good pump requires less work, so less amount should be here on the denominator, WSP. Denominator, yes. So, and that would be H2 minus H1 divided by, well, let's call all these points like actual. So H2 actual, right? And H2 actual minus H1 divided by, no, this is isentropic. Divided by H2 actual minus H1, if it was. And I'm looking for this guy. So, now, now what? That's a good question. Now, um, okay, we're looking for this guy. We have this guy. H1. Do we know anything about H1? No. Do we know anything about H2S? No. No. Okay. So let's find them. Let's solve for them one by one. Now, if we assume that the process was isentropic, I mean it is here in this question, but I'm just talking generally. Okay. Then we know that W, the work, isentropic work for pump would be H2S minus H1, which is in the other form, little v specific volume times the difference in pressures, right? Now, let's focus on this side. If I'm looking for this guy, and no, P1 and P2, do we have? Do we have? Yes. Doop, doop. And no. Okay. I can go at point 1. And at point 1, we have subcooled liquid. So we can use the saturation properties. I told you here up there that at point in this process, what was that? Here, see? Everything can be used there in saturation liquid. So I'm looking for V1. Point 1 is subcooled at what temperature? T1 75. Okay, so it's the VF saturated liquid at 75 degrees C. So if you go to table A4, then you can find this number. Once again, when you subcool something, you can use the properties of saturated liquid at that temperature. You remember I was talking about specific temperatures? It's right now, right here. I'm looking for H1. H1, what's the state of point 1? It's subcooled. Okay, so you can use HF at whatever the temperature is. Same table, A4. Gives you that. So, what are we looking for? We're looking, so now, see, we got that. Now we can solve for H2S. H2S equals H1 plus V1 times P2 minus P1. And now I have P1, I have P2, I got V1, I got H1. That's awesome. And these are 6,000 minus 50 kPa. And we have energy, but here we do not have, so we need to multiply this term, these two parentheses, by the conversion unit. And 1 kilojoule is 1 kPa meters cube. So H2S would be, so now you might be like lost, like why are we doing this? So I'm solving for H2S to go up there. H1 we know now it's HF at 75 degrees C, and we got that, we have this, so we know H2A, and then we got H3 and H2A. So if we put it there, that's the actual number, right? If they put them in there, here I got that, and I'm gonna solve this one, then I can solve for the question. That's it. That's easy. So I need to go to this equation and say that, okay, what is the efficiency for the pump? Hello, where are you? Here. 100%. Wow, such a good pump. So this is 1. Therefore, this is 1. And this cancels out. You might say, well, why did you solve for H1? Because I needed H1 to put it there and solve for H2S, and then now put it back there and find H2A. Therefore, H2 actual is H2 isentropic, which was 320.13 kilojoule per kilogram. Now we need to quickly go back to our table and update it. That H2 actual, which is 320.13 kilojoule per kilogram. Now to find the rate of adding energy in the boiler, we need to subtract H3 and H2 from each other. Therefore, Q dot in, which was m dot times H3 minus H2 actual, or whatever, because this efficiency is 100 in the pump, that would be 20. Now we have all the parameters on the right hand side, times. You can just check it out in the table. See, H2, H3, H2A, H3, we have them. Well, these lectures about cycles are so long. Thermodynamics is like always like that. It's like huge. And imagine when you design something, so kilogram and kilogram goes away. So when you are designing something, so imagine that you do not know all this specific pressure and temperatures, right? And then 59, and then you need to try and error. Do this, try and error, and then like, oh my god, that would be, you need to write like a code, you need to optimize, and you need to do all these processes 100 times. It's so difficult. It's, oh my god. Anyway, so I'm sorry about that it's long. So in part B, it asks for how much of work in pump is consumed. And we know that this is equal to this guy times W pump in, right? And okay, here it is asking for this guy. And we know that, right? It's just a difference between enthalpies here, right? We have these guys, and this is 1, so it's easy. So I can say, you know what? This is m dot times W pump isentropic, because the efficiency is equals 1, or even like times this, which is 1, and assuming pump is isentropically working, operating, then this would be the difference between enthalpies, and I know both, so it's 20 kilogram per second times. See now how helpful this, oh my god, summary table is. H1, I forgot to update H1 actually. I'm sorry about it. See, even sometimes I forget. So H1 is okay. Then that would be 320.13 minus 301.4 or 3 kilojoule per kilogram. Perfecto. Okay. And that's it, right? I'm looking for. Okay, so yes, I'm looking exactly for that. W dot rate pump in is 122 kilowatts. The next part, we're not, yeah, we're about to finish, I guess. So the next part is how much is the network? So the network is the difference in between how much of work is provided by the turbine minus how much of work is consumed by the pump, which would be W dot pump. Oh, no. Turbine out minus W dot pump in, right? This is solved, I know, but I don't know this guy. So I need to solve for, first I need to solve for how much work, how much rate, power is produced by turbine. And that is m dot times the difference between the enthalpies at initial and final states, 0.3 and 0.4a, not s, because the turbine is not working, operating isentropically. So that would be H3 higher enthalpy minus H4 actual. H m dot, I know. H3, I guess I know in my table, so, right? Yes, H3, but now I don't know this guy. So how do I solve for actual entropy at point 4? Sorry, enthalpy at point 4. Once again, one more time, we need to go for, what is it? The thermal or isentropic efficiency for a turbine, which is defined as the actual work divided by isentropic world, because in an ideal world, an isentropic ideal turbine gives us more work, so which is like isentropically working, operating, so it's more, it's larger value, it should be in the denominator. If you, just in case if you got confused, and that would be H3 minus, which is 94%. And I'm looking for H4A. This. I know that. Do I know this guy? Mm-mm. Anyway, so I'm looking for H4A, which is H3 minus 94 times minus H4S. And now I need to solve for H4S. I need to assume that what would the enthalpy at point 4 would be as if the process 3 to 4 was isentropic. So if we check our our equations up there, we need to assume first, assume that turbine operates isentropically. So the process would be 3 to 4 isentropic. So what does this mean? It means that we are coming right like down straightly, like vertically, from point 3 here to point 4s. And it means that entropy would be constant. So you remember now you know why I picked this guy, because now I can say that okay, you know what? At point 4, I just know pressure. That's all I know at point 4. See, he's lonely here. Point 4, just pressure. And we need to know another intensive property, which entropy can be. So by assuming that, okay, the process 3 to 4s was isentropic, it means that s 4s is s3, which we know that in our summary table. So we have another intensive property. So now we can judge that at point 4, which is in the middle of nowhere here in a mixture, now we can say, okay, so now if we check the table, we would know how much is the quantity, how much is x4s. Now, I know that pressure here is 50 kPa, and then the question is how much is the quality? Then if I know the quality, I can solve for H4S. And if I solve for H4S, then I can put it there and I can find H4A. And if I know this guy, then I can put it there and solve for total, I mean, the work produced by the turbine. Then I can put it back in the first equation and solve for net work. So let's come back. Don't be happy because we have not done any of those. But we will anyway. So I have entropy and I have the pressure. I need to go to the table and find some stuff. I need to find how much is the entropy at the saturated liquid at this pressure. How much is it, the entropy at saturated liquid phase? Okay, this is the entropy, kilojoule per kilogram Kelvin. And it's just if you go to A5, A5, where are you? F5, A5, there, at 50. Here, see? Here's SF, SFG, and SG. And I need SG. Then, if I know SG as well at 50 kPa, then I will be able to compare S for S, if it is, to compare and check if it is in between these guys, or if is it less than SF or is it higher than SG. Is it, let's see, 6.7, it's, oh my god, it's right in between. All at 50. So it's a liquid vapor mixture. We need to confirm. Listen to me. We need to confirm that it's a liquid vapor mixture. You cannot just assume, okay, you know what? I drew my diagram and then I ended up at a mixture. What? This was like roughly, that was estimation. But with numbers, you need to prove that, see, the entropy at point 4s is right in between SF and SG. So that's a mixture. Then you can go to the next step and solve for X4S, which is which you can use. You should use this equation. Then you'll say, you know what? This is my entropy. So here is the quality. Great. Now, if you go to the table that I showed you right now, just now, then you can solve for enthalpy at point 4s this way. And if you read, everything is at 50 kPa. Then the values would be, here are the values. At the same table, A5 at 50 kPa. Plus, here is the, what is it called? Quality times 2304.7 equals 2336.4. Okay, great. Now I have H4S. I can scroll up and see, okay, now I've got this guy. Now I can solve for H4A, actual entropy at point 4. Right there, that you have no idea where it is for A, it's just somewhere. Now you know exactly where it is by knowing enthalpy at that point. Now we know the enthalpy at the actual point 4 for A, the actual entropy at point 4. Now we need to, why are we doing all this? Because we're looking for the how much of work is produced by turbine. Now we've got that. Oh, I'm sorry. That is so long. Yeah. The cycle problems. So in previous lectures, I was talking about that. Like, remember those simple, tiny piston cylinder examples? Like how easy they were comparing to what we're doing right now. Oh my God. See? This is the real thermodynamics. And it is getting much more complicated when you don't know basically anything about pressure. You're designing. I mean, when you design, it's like like you need to optimize something that you don't know. So you need to solve for that several times to see what condition gives you the best efficiency. Now we found how much of work, the rate, is produced by the turbine. Now we can put it there and solve for the net work produced in the whole cycle. Now the net work is W dot turbine out minus W dot pump in that we found about an hour ago, minus this guy gives us U. Please just tolerate me a little bit more. I know that you want to know the answer and just close this page. So then it asks for the total efficiency for the whole cycle. And when you talk about the efficiency of the whole cycle, it's like, how much energy did I give you? Let's say you're talking to the cycle. How much of energy did I give you? Well, you gave me energy in the turbine, or like, I mean, no, sorry, in the pump. And no. I'm not talking about that. The supply. How much of, because I don't know, the pump might be on the same shaft, installed on the same shaft that turbine is. So I'm not giving you that energy. So so what? No. I'm giving you heat. Heat is valuable for me because I'm paying money for that. I'm buying the fuel. I turn on the boiler, and I'm spending money. That is the supply. Okay, so you gave me Q dot in the boiler. Great. And how much of work? I'm looking for work. I'm looking for shaft work. So how much of net work did you give me? Right? This is the efficiency. This is how we define the efficiency. So the net work divided by how much money you spent. The net work was this, and we gave this guy Q dot in, Q dot in, Q dot in. Where are you? Where are you? Here. Oh my god. We gave this cycle 59,660 kilowatt, and it just gives us that much? Oh my god, it sucks. 30%. That's super low, but this is the nature of Rankine cycle. It's so super difficult to enhance the efficiency of these cycles. Thank you so much. Thank you so much for listening to this lecture, and that's it.